board. Okay, so welcome to the first day of class. Calculus 3 in 25 words or less. What is it? Calculus 3 is essentially Calculus 1 all over again, but in 3D. Yeah. So the two things that you should have learned in Calculus 1, let's briefly go over those because that's what you're going to be doing here in Calculus 3. In Calculus 1, you did two big things. Well, you did a lot, but I claim the two biggies are the one thing that you did is if you have a function, say y equals f of x, and you're looking at the graph of it, and somebody says, hey, right there at that point, pick some point, and if I draw a tangent line to that point, I want to get the equation of that tangent line. Do you guys remember doing that in Calculus 1? Yes, no? I'll check the chat. Yay? Are you guys there? Hello?
Yes.
Okay, just checking. I wonder why I can't see my chat box. I'm gonna have to see something here real quick. Here we go. There it is. Okay. Yes. Okay, great. So how would you get the slope of that tangent line? So here's the tangent line right there. How do you get the slope? Anybody? Don't be shy. I'll unmute you. Okay, how about if I call on somebody? You want me to do that? There's 12 of you in the room. Okay. How about Alan? Alan, are you there? Can you hear me?
Hello?
Okay. Hey, Alan, how are you?
Okay.
Good. I know you're probably still trying to wake up. Do you remember how to find the slope of a tangent line?
I forgot like everything. I need like a quick refresher.
Okay. Does anybody want to jump in and give Alan a hand?
Yeah, I can.
Okay, great. Go for it.
You would find the derivative and then evaluate it at the point, and then
Good.
you
You're
to
going to
get
have some x coordinate, and so it's going to be the derivative evaluated at that point. Yeah.
yeah.
Oh, okay.
Does everybody remember this? Sort of. Okay. All right. So who was just talking to me? I didn't see who was it.
It was Jake.
Jake. Okay, Jake. Yeah. Thanks so much for that. You're absolutely right. So that would at least get you the slope of that tangent line. And if you forgot everything, not to worry, I have some review videos on my Canvas account. You may want to take some moments like this afternoon and just perk your brain up and review some stuff. Okay, so that was one thing you're supposed to do. I'm not going to go get the full equation of this tangent line, but what we're going to do in 3D is instead of working in the 2D, you're going to be in 3D here. So you're going to have an X and Y axes as well as a Z axis. And instead of the graph being a curve, you're going to have the graph be some surface. Say, I'll just try to draw a surface like this. Can you imagine this being a surface? And so I'm going to pick a point on the surface, I don't know, like say right there. And instead of drawing a tangent line, I'm going to draw a tangent plane. And you're going to have to get the equation of the tangent plane. So that's what we're going to do in 3D. The other thing that you did in Calculus 1, and maybe you forgot, but I'll remind you, is the other biggie is if you again have some function, say y equals f of x, one of the things you did in there, besides taking derivatives, was you would find, say, area under the curve. Does anybody remember doing that? Yeah?
Yes.
Okay, yes. Good. And does anybody remember that area involved taking the integral?
Yes.
Okay. So how does that work in 3D? Like, what are we going to be doing? Well, instead of area using a single integral, you're going to be, again, you're going to be given that surface I told you about in 3D. So this surface right here. And then you'll be asked to, as an example, there's more, you'll be asked to find the volume of the solid that's formed where that surface is sort of like the capping surface. And so you're going to be doing volume, and the volume will be found by doing either a double integral of the function or a triple integral. Yeah, you see that where you put two integral signs right next to each other, or three? Yeah, we're going to be doing that. Not for a while, but that's where we're headed. Okay, so that's basically what we're going to be doing in Calc 3. That's a very simplistic look at it. But as I mentioned in my welcome letter, we're not going to be doing calculus for 2 weeks because we're going to focus on learning what vectors are and how to have fun and play with vectors, because that's an integral part of this course. Okay, so let's get to it. We're going to start in 2 dimensions, and then we'll work our way to 3D as the week progresses. So what the heck? Vectors in the plane. And the word plane does not mean a jet plane. From now on, for the rest of the semester, know this vocabulary word, folks. The word plane is going to mean 2D, 2 dimensions. So anytime somebody says in the plane, you'll know, oh, we're working in 2D instead of 3D. Fine. So we're going to learn how to do 4 objectives here. And so we're going to start with learning how to work with the component form of a vector. But first we have to define a vector. So let's do some introductory definitions. Scalars. What are scalar quantities? Scalar quantities are physical quantities that can be characterized by a single real number. Write this in the blank. And if you don't have your course reader yet, when you watch the video again, which I would if I were you, start filling in the blanks. So what's some examples of scalars? And scalars are just pure real numbers. Well, length, area, volume. Those are 3 examples of scalars, because, you know, to describe the length of, say, you know, the dimension of the length of a table, you would just go, oh, well, my table is 3, you know, as in 3 feet. Okay. So what about vectors? Vectors are different from scalars. So vector quantities are quantities that involve both a magnitude and a direction. Now, what the heck? Magnitude is a fancy word for length, although it may not mean length if we're working in 4, 5, 6, 7, or 8, 9 dimensions, which this class doesn't do so much, but linear algebra you will. Okay, and direction is just what direction is the vector pointing to. So what are some examples of vector quantities? Forces, if you're taking a physics class, it's all about vectors, because forces are described by vectors. Velocity is a force, so it can be described as a vector, and same with acceleration vectors. Okay, so now let's take a look at some visualizations of a vector. So a vector is essentially a directed line segment. That's all it is. Fill in the blank. A directed line segment. That's how you represent a vector. And here's a picture of a vector right here for you. There's a picture of a vector. So what we're going to do in this little picture is let's label the tail. That's the initial point. And we're going to label the terminal point, which is also known as the tip. Okay, so the A here, this point here, I'll put a little dot, that is known as the initial point, which is also known as the tail. The B here, the tip of the arrow, if you will, is known as the terminal point, and that is known as the tip. So right there is the tip of your vector. Now let's talk about notation, which is really important, because when you take quizzes in my class, you're going to do handwritten work, and I'm going to want to see your proper notation for you to get your full credit, right? Okay. So the notation for a vector that we just drew that has an A as initial point and B as terminal point is AB, with a little arrow on the top. You see that arrow on the top? You got to put that there. And order matters. So the vector AB is not the same as the vector BA. They point in opposite directions. The only thing these 2 vectors would have in common is their lengths, which is also known as magnitude. Textbooks, as well as my math lab, when you're doing your quizzes and exams, they're going to use boldface to denote a vector. They won't necessarily have a little vector on the top of the vector notation. So the vector AB might be called V. See how it's in boldface? It's darker and without the arrow on top. And it's customary to name vectors using lowercase letters. That's the tradition. We're going to stick to it. Once in a while, you might see that guideline violated, but very rarely. Okay, now when you do handwritten vector notation, required, otherwise you're going to lose points on quizzes exams. When you denote a vector by hand, you got to put a hat on it, put the little arrow on top. So for example, I do like this, so it doesn't look like a full arrow. I'm okay with that. Or if you want to put the full arrow like that, that's okay. But if you just go like this, V, without the little arrow on it, I'm going to dock you 1 point every time you do it. So let's say on your exam, you had to write it down 20 times. I could take away 20 points from you for not doing your arrow. That's not good. So put an arrow. Okay, let's move on. Key weird fact. It's not that weird, but a lot of students lose sight of it. Anytime you see a vector, a picture of one, or somebody's talking about one, it actually represents a whole infinite set of vectors. All the vectors that have the same length and magnitude, okay? And I should put direction, okay? Okay, so let's talk about standard position. What is standard position and why do you care? Well, if you just draw a vector sort of out there in the universe like we did up here, that's known as a geometric vector. He's sort of out there, you know, flapping in the breeze or whatever. When we put a vector in standard position, what that means is we're going to have a coordinate system, typically the rectangular coordinate system to start us out with an x-axis and a y-axis. And we basically move the vector so that the initial point is located at the origin. And since we're going to start working in 2D, you know, you're just going to have an X and Y axes like this. And so that just means that you're going to position your vector so that its initial point is sitting right on top of the point 0, 0. Okay. Now let's talk about component form, which is my personal favorite. And here's the definition. If a vector V is already in standard position and you need it, and otherwise component form is meaningless, then your vector V can be written with these angular brackets. And yes, you're going to have to use angular brackets in the class. And then a number, which I'm just calling V1 right now, comma, and then some other number, V2, where those numbers, V1 and V2, are called the scalar components. Scalar components of V. By the way, my handwriting is not so good. So if you ever have trouble reading my handwriting, please don't hesitate to interrupt my lecture and say, hey, professor, hey, I can't read your writing. What the heck? So does anybody see that says scalar components?
Yes.
Okay. So, oh, I saw somebody from before. Nathaniel, you said y equals mx plus b. That would have definitely have been the tangent line equation. Yes, where m is your derivative. True. Definitely. Okay. Scalar components of V. And when you write your vector in this format, it's known as component form. There is another format that I do want you to be comfortable with. It's usually what our physics brethren use. And we'll talk about that soon, not yet. The zero vector, and there is such a thing, is denoted with a 0 with a little hat on it, little arrow. That means the zero vector. That's very different from the pure number 0. So if you mean the zero vector, but then you just write a 0 down on your paper, I'm going to dock you points. Because the number 0, this is the number 0, is a scalar, aka pure real number, whereas the zero vector is a vector. The way you'll denote it in component form using the angular brackets, and then the scalar components are simply zeros. Okay. What does the zero vector even look like? If I had to graph it, I'm serious, what would it look like? It doesn't have a magnitude. It's zero magnitude, basically. So it's, if somebody says, what's the magnitude of the zero vector? Or what's the length? It's 0. So it's just a dot sitting at the origin. Well, I thought you said a vector looks like a directed line segment. You know, it's got a little arrow on it. I lied. Every vector except the zero vector looks like a directed line segment. Okay. And yes, the zero vector is very important and it comes up a lot. Okay, how do you find the length of a vector? Because that's one of the first things I'm going to ask you on quiz 1 this coming Sunday. I'll give you a vector in component form and go, hey, what's the magnitude? And it's super easy because here's the deal. Once you're given a vector in component form and somebody said graph it, all you would do is you would find the number V1 on the x-axis. Let's say it was right there. And then you would find the number V2 on the y-axis, let's just pretend and say it's right there. And then you would locate the point V1, V2 right there. And then to draw the vector V1, V2, you would start here at the origin and then draw a directed line segment so that the arrow ends up at the point V1, V2. That's all. And there, I just drew the vector V1, V2. Now, how do you get the length of this vector? I hope you can tell that we're really just going to be using the Pythagorean theorem to get the length. Because if you drop a perpendicular down from the tip down to the x-axis, and you notice here's a right triangle, and then here is the x length of your, and that basically would be V1 essentially. And then the other leg's length is simply V2. And if somebody says, what's the length of the hypotenuse? Hey, that is just the square root of the sum of the squares of the components. And so please memorize this formula. I mean, I let you use notes for quizzes and exams, so you can have your course reader with you at any time when you take your midterm or your final or your quiz. In fact, I encourage it. Like, take good notes so that you can have your course reader ready to go and use, you know, all your notes to help you on your quizzes. Now, if you don't know the material very well and you're always thumbing through your course reader to find answers, that's probably going to cut into your time for your quiz. But so that's kind of why I'd like you to memorize the magnitude formula. Now let's talk about notation. If I ask you to find a magnitude, you'll see these double bars on either side of your vector notation. Although Briggs, our textbook, tends to use single bars instead, which I don't like so much because it almost looks like somebody saying find absolute value. And there's no such thing as absolute value of a vector, okay? You can only take an absolute value of a pure number. So know your magnitude, and it's basically just the Pythagorean theorem in action, okay? I'm going to pause here for a moment. Does anybody have any questions or concerns? I'll look in the chat. Anybody lost? Are you guys awake?
Yes.
Okay.
Yes.
I'm just checking.
Yeah.
You know, I've just found sometimes when I'm Zooming, I get that a lot of people, it's easy to zone out during a Zoom lecture, you know, because I do it during meetings. I know how that's like. And it takes almost all your energy to just stay focused and awake. And it is kind of early in the morning too. So hope you have some tea or coffee to get you going, right? Okay, another thing I'm going to ask you to do on Sunday's quiz. Sunday's quiz is going to be pretty easy, folks. I'm not going to kill you. It's going to have maybe 7 or 8 problems, and it's just going to cover the first 2 sections. And if you're getting some of these basics here, you're going to do just fine. Okay? But you got to get the basics. So here's another basic fact about vectors. If somebody gives you the initial point's coordinates, and it's not the origin, and somebody gives you the terminal point coordinates, how would you get your vector? So let's say somebody gave you the P and the Q points, how would you get the vector PQ? Now notice when we denote a point in this course, we're going to use parentheses like an ordered pair. And you should be familiar with that from algebra. You know, ordered pairs are denoting points and you use parentheses. But when we denote a vector, in order to distinguish it so we don't get confusing vectors with points, you want to use these angular brackets. And then how do you get the x and the y here? Those are the components of your vector PQ. You're going to do what I call terminal minus initial. Terminal minus initial. What the heck are you saying? We're going to do some examples, so don't worry. But the two formulas that I also would memorize if I were you is the x is going to be simply found by taking the difference of the x coordinates of the point P and Q, and order matters. You want terminal minus initial. So the terminal point here they're saying is Q, so x2 minus x1. And then the y component is simply the difference of the y coordinates of your 2 points, but order matters, y2 minus y1. So let's do an example, and here we go. So I'm giving you a point A and a point B, and we're going to do 3 things. We're going to find the component form of the vector AB. We're going to find the magnitude of AB. And then we're also going to sketch the geometric and the algebraic vectors on the same graph. Well, what's the difference? The algebraic vector is the vector that's in standard position. That's where its initial point is located at the origin. Okay, and I'm going to do these out of order. So I'm going to actually graph the geometric vector first. So let's do this first. So what do I mean? Well, just plot the point A and plot the point B and connect the dots, making sure that B is the point that gets the tip, the arrow. Okay, so that's super easy. Find the point 8, -3. Okay, there it is. There's the point A with coordinates 8, -3. Find the point B. Okay. There's 4, there's 5. So the point 4, 5 is up there. That's the point B. And then just draw an arrow connecting the dots. Well, that's not a very good straight line, but I think you get the idea. That's called the geometric vector. There he is. And do you see he's sort of pointing up and to the left a little bit, and he's not too big of a vector, but you know, you want to find this magnitude, the length, but not yet. We're not going to do that first. The first thing I want to do is get this vector into component form, because then I can use the magnitude formula quickly. So how do you get the component form of AB? You're going to do the quick formulas that I just showed you up there, right here. You're going to do that right now. Okay, so you're going to take the difference of the x coordinates, and order matters. So you're going to do terminal minus initial, so 4 minus 8, because B is the terminal point and A is the initial point. So take the difference, and then take the difference of the y coordinates, 5 minus a -3. And you guys know subtracting a negative is the same as a positive. So the component form for this vector AB, so this right here is the answer to part A, right here. I want the brackets and then a number, comma, a number. Okay, -4, 8. Any questions so far? Everybody okay with this? Now, go ahead.
So we're using like these greater than or equal to symbols instead of like the hard brackets or soft brackets instead?
Yes, exactly. On your keyboard, yeah, greater than or equal to, or excuse me, greater than or less than symbols. Yep. Those
Okay.
are the angular brackets. Very good, Nathaniel. You got it. Yeah. Now, is anybody in the class? Let's do a quick survey, and you can just tell me in the chat. Quick little informal survey. Anybody here taking linear algebra this semester, math 254? Or did you take it maybe last semester, math 254? Anybody? I'll check the chat, or you can scream. Hannah says no. Aaron says taking it this year. So Aaron, are you taking it this semester? Or
Yes.
maybe, okay, you're taking it right now. Okay, cool. No, no, no. Everybody's a no, okay? Okay, so Aaron, I'm talking to you, but I'm actually talking to the other folks in the class. Other folks in the class, even though you may not be taking it now, you will be, because it's an important class, especially if you're a computer science or electrical engineering degree. Linear algebra is required. What is linear algebra? It's not your mama's algebra. It's a very conceptual course. I've taught it multiple times. So Aaron, if you have any problems and you'd like to come to my office hours and ask questions about it, come on down. I'd love to help you.
Okay.
It starts off real easy where you're just working with matrices and solving linear systems. So the first 3 weeks, you're like, oh man, this class is going to be so easy. I know how to do all this solving systems and matrices are easy. And then pow, you get really conceptual and you start doing vector spaces and inner product spaces and crazy stuff. I actually will claim that this class will help you do that class better. So Aaron, take good notes in this class, you'll be fine. But the reason why I'm bringing it up is in that class, at least the textbook, they like to denote vectors using parentheses. And so, which is unfortunate because we're using parentheses for points, not vectors. But in that class, they just want to use parentheses for vectors. It's very confusing. And if you're trying to take both classes at the same time, it could drive you nuts. Anyway, that's just an aside, but we want to use the angular brackets, which is like the less than or greater than symbol. Okay. Any other questions? Did I answer your question okay, Nathaniel? Yes, no, maybe? Okay. All right. Now, how do you graph this component form? Well, you just find the point -4 right there, and then you find the point 8, which is up here, and then you plot that point, which is way up here. There's the point -4, 8. And then you just draw, starting at the origin, because component form, it's understood the initial point is at the origin. And there's the vector AB. That's what we call the algebraic vector AB. Well, which one of the vectors is AB? They both are. One of them is down here and just sort of out there, not in standard position. And the other one is in standard position. They're both really the same vector. Remember that key weird fact I told you about? That every single vector that you see is representing a whole infinity bunch of vectors as long as they share the same magnitude and they share the same direction. And so there you go. Those are really the same vector. Okay, now let's go get the magnitude. So how do you get the magnitude of AB? You're going to take the square root of the sum of the squares of the components. This is essentially using the Pythagorean theorem, essentially is what you're doing here. And it's pretty easy. And you'll get square root of 80, and I'll mark you off 1 point if you leave it as square root of 80. Why? I like you to simplify your radicals completely. Please don't give me the decimal version. I like exact answers unless I specify I want the approximate decimal. Since 16 is one of the factors of 80, then that's a perfect square. You can simplify this radical, and that's the final answer. Okay, so that's the magnitude, and we're done with this problem. Any questions?
Yes, I actually have a quick question.
Go for it.
In terms of, well, I think, well, I don't know if I can answer my own question, but because it's a vector, right? There's no units, correct?
No, there's no units.
Okay. Cool.
No. Now there may be, if you were, when you're working with physics and you've got a vector that's a certain length, and maybe that length is representing feet or meters or so on, then you would have some sort of units here. It would be feet or meters or inches or what have you. But because I'm kind of working in this unitless rectangular coordinate system, we'll just not have the units. Is that okay?
Yeah, thank you.
You're welcome. Any other questions?
Is that a 4 or a 9 for the negative?
What's that?
Is that a 4?
This right here?
Yeah, the negative.
Yeah, that's a -4 getting squared.
Alrighty. Sorry.
Yeah. So it's going to be, anytime you square a negative, it's positive, right? So.
Right, yeah.
Yep. Okay, I'm going to keep going. Let's talk about something that a lot of students just go, yeah, whatever, and then they don't get it. It's super important, and it's going to save their behind on many problems. This, I would put a star. I'd put a few stars by it, even though it sounds like duh, obvious, like, wow, Captain Obvious, folks. Your two vectors U, let's say you were given some vector U and it had some components U1 and U2 and some other vector V, V1, V2. Let's say somebody said, hey, those two vectors are equal. Really? If they are in fact equal, that can only be true if their components match. That would mean that U1 is exactly the same number as V1. And that would mean that U2 is exactly the same number as V2. And that would be the only way those two vectors could possibly be equal. And I know that seems like, okay, well, that makes sense. I'm fine with it. Let's move on. Yes, it does make sense. And you need to know it. You'll see in this lecture that it's going to come and save us on a couple of occasions. Okay, so let's keep moving on. Let's fill in the blanks for some vector operations. These are kind of obvious, but they're very, very key and important. So let's do some definitions of fun and play with vectors. When you have vectors, a lot of times you want to add them together, or maybe you want to multiply them by a number. And so we're going to look at vector addition and what we call scalar multiplication here. And this is super important because you got to know how to have fun and play with vectors. Sure, it's nice to draw one and figure out its magnitude, but that's not all. So what if somebody said, hey, I got U and V, I got it. Those are the two vectors, U and V, they're given to me. And somebody says, hey, add them together. Okay, it's very simple. You are going to form what's called the resultant vector. Adding two vectors together is going to give you a vector. And the first component, which I will call the X component, if you will simply be the sum of the two X components of these two vectors, comma, and then the Y component is just going to be the sum of the Y component vectors of components of these two vectors. And you're done. And there's your answer. Super easy. We'll do some examples in a bit. Or you will. Okay, how about scalar multiplication? What does that mean? Take some scalar C, that's just a pure number, some real number, could be positive, could be negative, and you multiply it with the vector. And so in the intermediate step would look like that. And then what you do is you simply, I don't like to say distribute, but I'm gonna, you essentially distribute the scalar so that he's multiplying with each of the components, and you get a resultant vector, and you're done. Now, what's the negative or opposite of a vector? It's opposite of V, and it's the same as multiplying the vector with a scalar of -1. So you just distribute the -1 essentially, and you vector with components -V1 and -V2. And visually speaking, it's just going to be a vector of the same magnitude pointing in the opposite direction. Okay, now what about subtraction of two vectors? No problem. Here's the intermediate step. And then you're going to get a vector, and you take the difference of the X components to get the new X component of the resultant vector, and you take the difference of the Y components to get the Y component. And that's basically it. So before we do an example, I want to do the visualization of addition, scalar multiplication, and subtraction, and then we'll do some examples, okay? So now that everybody's here, I want to just do a quick pause here, resuming the recording. Okay, so here we are, we're back at it. All right, so let's talk about the different ways you can visualize adding two vectors together. And this is really going to help you, especially if you're in physics right now, or you're going to take physics. I always tell my students to take Calc 3 before physics, because you'll have a better chance of acing it. Okay, so let's say you had a vector U and some other vector V way the heck over here. And somebody said, hey, I want you to add U plus V. You're like, oh, really? What you're going to do is you're going to translate one of the vectors, and I'm going to translate V over. So I'll just redraw U.
Professor Reski?
I think you're
Yes.
sure.
Sure.
Yeah, you're not sharing the guide. We can't see what
Oh, you
you're
mean I'm not
typing.
sharing my screen?
Yeah.
Oh, man, what's wrong with me? I'm sorry. Oops. I guess when I stop the recording, I have to go share the screen again. My bad. I apologize. Thanks for pointing that out. See, that means you're alive. Yay. Woo. So here's U. Here's V. Somebody says add them together. Ugh. What I'm going to do is I'll redraw U right here, and I'm going to translate V. Remember, as long as V maintains its integrity, that is the direction it's pointing and its magnitude, I can move it anywhere I want to. So I'm going to move it in such a way, oops, I wanted to do tail to tip method, sorry. I wanted to put his tail on the tip of U like that. That's why they call this the tail to tip method. So I translated him. Now what? Well, the U plus V is going to be where I connect the tail of U to the tip of V. This red vector here is actually the resultant vector. We call that the resultant vector of U plus V. And I'm done. That's called the tail to tip method. Now, there's another way to visualize U plus V, and I want you to know that way too, so you can be totally smart when you go take vector calculus over in UCSD or San Diego State. There's another class after this one. We don't teach it here at Southwestern. It's the next in the calculus sequence, but it's called the parallelogram law. So let's just say here's U, and here's V way the heck over here. Oops. And somebody says, hey, add U and V together. And you're like, okay. You're going to translate V again, but this time, let me redraw U. So there's U again. He's just lying flat. I'm going to translate V so that both their tails touch. And now what? What's this have to do with parallelograms? They call it the parallelogram law. If you can imagine right now that these two vectors are adjacent side lengths of a parallelogram, so I'll draw the other two missing sides. The U plus V is simply the diagonal of the parallelogram. There it is in red here. This is the vector U plus V. Can you see that it's the same as the tail to tip method? You end up with the same vector pointing in the same direction and essentially the same magnitude. Well, which way is better? That's not the question you want to ask because it doesn't matter. They're both fine. They both just visually show you U plus V. You're typically not going to be drawing pictures for me, but if you were taking a physics class, this is really helpful so you can get a feel for what the heck U plus V is even doing. All right. Now, what about vector subtraction? Well, you know that subtraction is really the same as addition because you can change it into adding a negative. Isn't that true? So if somebody said, oh, I want you to do U minus V, so here's U, here's V again. All right, fine. One way to do U minus V is to connect their tails, and then U minus V is I want to try to switch colors here. U minus V is the vector that, oh, that looks terrible, is connecting the tips together where you're pointing in the U direction. If you were doing V minus U, it would go the opposite direction. So what do you mean? So if you had U right here and V right here again, V minus U would look like this. Now, what does that got to do with addition? Well, I haven't done that yet, but I just wanted you to see visually what subtracting vectors does. But how would you look at it this way? Okay, so what you would do is you would draw U in the usual way. So here's U again. There he is. And then you would draw the opposite of V. So I'm going to have to draw V sort of pointing in the opposite direction like that. There's the opposite of V would be this vector here. Okay, so there's V, and when you draw something in the opposite direction, it's just same length but turned 180 degrees. And now what? Well, if I use the parallelogram law again, now that I'm adding, and think of these two vectors as being adjacent side lengths of a parallelogram, and then draw the diagonal, that's U minus V right there. And I hope you can see that this vector and this vector are equivalent. They're the same vector. Yeah, and I'm done. Now, let's take a look visually what scalar multiplication does to a vector. So let's say you multiply a vector by 2, say. What does that do to the vector? So let's draw the vector in standard position just so you can kind of see what happens. Let's say you had a vector here, V. There he is. He's really cute. And let's say somebody said, I want you to do twice V. Fine. Twice V is just going to be a vector that's twice as long as V and pointing in the same direction. There's 2V right there. What if somebody said, well, I want 1/2 V instead? No problem. It's going to shrink V, and so it'd be the vector pointing in the same direction as V, but half as long. So that green vector I have there would simply be 1/2 V. And then you can also multiply by negative numbers, like what does negative 2v look like? Well, it'd be the same length as the original v, or twice rather, the original length of v, but pointing in the opposite direction. So this big green vector here would be negative 2v. So he's just pointing in the opposite. Okay, so that's scalar multiplication. It's either stretching a vector or shrinking a vector, essentially. And we're done with that. Now let's do some examples. Okay. I'm going to let you guys do this. Well, what do you mean? Well, you know, I think you can work on this. So I'm going to put you in pairs in breakout rooms for fun. And so let's see, we've got 12 people in the room. Good morning, everybody. And let's see, I'll create 6 rooms. So we'll have pairs. And I'm going to create the rooms and then I'm going to open them. And then you need to go into your room and then say hi to your buddy. I'm going to encourage you to please, you don't have to turn your video on if you're, you know, didn't comb your hair or whatever, but please, if you can, turn your microphone on so you could talk to your buddy and work together on the problems, because I want you to try doing A, B, and C together with your buddy, okay? And I'm going to go to the rooms and check on you guys and see if you're stuck or not, okay? I'm creating the rooms right now. Woohoo! I'm going to open all the rooms. Okay, see ya, everybody. Go for it.
Yes.
Okay, so somebody tell me what happened when you took 2/3 of u. So hopefully this is an intermediate step.
We distributed it.
Plug them in.
Okay, yeah, so you actually said I'm going to do 2/3 times -3 and then 2/3 times -8 and then simplify. So what was your final answer? Did anybody get it? Put your angular brackets here with a comma. What'd you get for the first component? Anybody want to be brave and tell me?
Got -2.
Yep.
-2.
Good. And how about the y component?
It was a fraction.
Yes.
-16/3.
Good. Yeah. No decimals. -16/3 is what I want. Did everybody get this for letter A? Component
Yes.
form? Okay, we're good. Okay.
I don't know if you're sharing your screen. I don't think.
Am
you
I
are.
not sharing my screen again? Gosh darn it.
Yeah.
Uh-oh.
I keep doing that. I keep doing that. Why do I keep doing that? I don't know. Hold on a minute. I have to keep going back and forth. Okay. So back to where we are. So hopefully you got there. I did some intermediate steps here because I thought I was sharing my screen and I wasn't. Okay. So if you got -2, -16/3 with inside the angular brackets, you're doing good. So with v minus u, you're simply going to take the v vector and then subtract the u vector, and you should get a vector where you're going to take the difference of the x components to get the new x component and the difference of the y components to get the y component. So your final answer after you do the arithmetic is what? 11 and 33. Did everybody get that?
Yes. Yes.
Now, letter C is a little bit tricky. Why? Because you're being asked to do scalar multiplication and vector addition at the same time. And you want to approach it the same way you would with real numbers, where the multiplication takes precedence over the addition. So first you'd want to do 2 times the u, and then you'll add that to 5 times your v. So if you were doing this in slow motion, this would be an intermediate step. So then you're going to basically get, when I do the scalar multiplication first, I'll get -6, -16. And then when I distribute the 5, I'm going to get the vector 40, 125. And now I can do the sum of these two guys. And so I'll get what, -6 plus 40 as the first component, and then -16 plus 125 as the second component. And then I got to do some more algebra here, or arithmetic rather. And did we get 34,109?
Yes.
Okay. So did anybody try letter D? Because it's hard.
We read the problem.
I'm going to do it, but I do want to tell you, I will put this on a future quiz or exam. You should know how to do it.
Oh,
It's not that hard after you see it done once. I mean, the first time you see it, you might go, oh my goodness, I would have never thought of that. But if you are taking a Math 254 class, they ask you to do this all the time. And it's a skill that's like, you know, like you should know how to do it. So what is it? They're basically giving you a vector W. And they're telling you you're supposed to find a couple of pure real numbers, scalars A and B, such that W can be written as a linear combination of the vectors U and V. And that's a key phrase right there, linear combination. You're going to see that a bit this semester. In other words, they want you to find A and B such that W can be written as A times U plus B times V. That's the goal. And it's a little bit involved because you're basically saying that this vector 1441 needs to be written as a scalar times -3, -8, plus some other scalar B that's unknown, 825, like this. And now I'm doing this in super slow motion to make a point because you'll see in a moment why. When I distribute the scalar for the first vector, like so, and then I distribute the other scalar B, so I get 8B, 25B. And then here, I'm going to add those two vectors together using my knowledge of vector addition. So add the X components to get the new X component. And then add the Y components to get the new Y component. And that still has to equal the vector on the left-hand side. And folks, this is where equality of vectors comes into play. And I pointed it out up here. Remember I said this is going to save us? Right here, it's going to happen. We're basically saying two vectors have to be equal to each other. The left-hand vector has to equal the right-hand side vector. How is that going to occur? What has to occur is these components must match. The X components have to be the same guy. So I write 14 is equal to -3A plus 8B. And then similarly, the Y components have to match. That's got to be required if we have equal vectors. And folks, this is a two equation, two unknown linear system that you probably learned how to solve in a baby beginning algebra class. And I'm not going to solve it here because I think you guys know how to use either the substitution or the elimination method because I'm kind of short on time. I'll just say you do it. And then the correct answer, if you do it correctly, hopefully, is you get A is -2 and B is 1. And what does that mean? It means that the W vector, the original vector they gave me, can be written as -2 times U plus 1 times V. That's all. Well, why is that important in the linear algebra class? Well, you got to take linear to find out why that's super important. Okay, moving on, let's do a theorem and fill in the blanks. Properties of vector operations. These are kind of obvious, but you have to be careful because you can't assume. But suppose you have U, V, and W, and those are vectors in the plane. What does plane mean again?
2 dimensions.
2D.
2D, thank you. And let's say C and D are both scalars. That just means they're pure numbers. Fine. Then it doesn't matter what order you add vectors together in. U plus V will always give you V plus U. It's commutative. Nice. What about if you were adding 3 vectors together simultaneously? Well, there is associative property. You could add the U and V together first. That's where the parentheses, then add W. Or if you prefer, you could add the V and W together first, then add U. It doesn't matter. It's all the same. What if you take a vector U and add the 0 vector to him? Notice this 0 is in boldface, which means it's the vector 0, not the pure number 0. What do you think your result would be? What happens when you add the number 0 to say 10? What's 10 plus 0?
10.
So U plus 0 should be
U.
U.
Hey, good job. Okay, how about U plus -U? You know, like 10 plus -10 gives you what?
0.
0.
So U plus -U gives you
0.
almost 0.
Vector.
You? Oh,
Vector.
ah.
You'll have the vector, yeah. And if you're multiplying two scalars with a vector, that's legal. You can either multiply with the first guy and then multiply the second guy, or if you prefer, whoopsie daisy, sorry about that, you can multiply C and D together first, then the U. It doesn't really matter, the order. There's distributive property with scalars. You could distribute here. This would be the same as CU plus DU. Either way, they're both left-hand side and right-hand side are the same. Here, if you wanted to multiply a scalar with two vectors being added together, you could add them first, then hit it with the scalar, or distribute, your choice. If you're multiplying any vector with a 1, you're just going to get the vector. That's the identity. And any vector multiplied with a 0, you'll get the 0 vector. Okay, fine. Pretty easy peasy. It's what you'd expect. Nothing fancy there. Let's move on and talk about what happens when you stretch or shrink a vector with this scalar, which we talked about what it does visually. What does it do to its magnitude? Well, as we saw visually, it either stretches or shrinks the length, the magnitude. But what's important is that magnitude is always a positive number. So if you have a scalar, and it could be a negative scalar like -2 and v is a vector, and somebody says, hey, look at this new vector, CV, which could either be stretched or shrink, what's that magnitude? In other words, and there's the notation asking you to find magnitude with the double bars. Well, you could either find the magnitude of the vector as is, or if you want to make it a little easier on yourself, just take the absolute value of the scalar and then multiply that with the magnitude of the original vector. You'll get the same thing. Same thing. Okay, theorem. Now this is super important. Put stars all over this. Oh my God, this is for sure, people. It's gonna be on the quiz Sunday, okay? Like for realsies, like I'm not kidding. And it's real easy, but you gotta be awake. And I know we've been here with an hour and 15 minutes, and I'm probably gonna go for at least another 10 minutes. So please try to stay with me, okay? And a lot of times I do go overtime, okay? I get you may have another class. Don't worry, I'll finish plenty of time of that, but a lot of times I kind of like to finish up a topic or a thought and just think of it as free education. And if you're already dead and you're asleep, just watch the video recording later, okay? What about getting a unit vector pointing in the same direction? You're going to be doing this all semester long. In fact, I'm going to ask you to do it on the final exam also. That's how important this is right here, okay? Yeah, it's going to be on the midterm, it's going to be on the final. It's never going away, this concept right here. If you're given a non-zero vector, a lot of times they want you to shrink or stretch, depending on the original vector, the original vector so that it's 1 unit in length, okay? And this is the formula right here. You take the original vector and simply divide by its magnitude. So your vector will be whatever the first scalar was divided by the magnitude, and comma, and then whatever the second scalar component was divided by the magnitude. That's all. This is called a unit vector. The unit vector has a magnitude of what? 1. That's what the word unit means. 1. Unit vector. And it points in the same direction as the original vector. It just has, it's the magnitude length has been forced to be a 1. And you're going to do this all semester long. Well, why is that so important? That seems rather silly. I can't tell you. That's why you have to take the class. You'll see over and over again why having a unit vector is key, especially if you're doing projections. Okay, some vocabulary for you. When you multiply a vector by the scalar 1 over its magnitude, sometimes the book will call this normalizing the vector. In this class, I'm going to refer to it as unitizing the vector. By the way, that is not a real word, unitizing. I didn't make it up. My mentor, Professor Arnold Vallone, who is deceased, he actually died, today is his anniversary of his death, 2013. He was a great man, but he would call it unitizing when I took his vector calculus class. So now I'm just sharing it with you. Okay, unitizing. So let's do an example, and we'll finish off today's lecture with this example. Okay, so just stay awake for example 3, and then you could go take a nap. Well, again, if you want to talk to me today about anything, I have sort of just an emergency office hour today at 3. You're welcome to come. Normally Mondays I don't have office time, but if you want to chat, 3 o'clock. Okay, so here's a vector 3, -1. We're going to do some stuff to it. Before we do anything to it, even though they're not asking me, let's just sketch it so I can reiterate how you sketch a vector that's given to you in component form, so you know. How would you sketch the vector 3, -1? Anybody
Start
remember?
at the origin and then plot the point.
Okay, good. Plot the point, 3, -1. There it is. There's the point, 3, -1. And then what? Is that, am I done? Is that the vector?
And then draw a line from the origin to the point with the arrow at the point.
Good. There's my vector. Isn't he cute? Yeah. He's so cute. Okay, so that's my vector. All right, now we're going to find a unit vector that points in the same direction as our v. So we first are going to have to get the magnitude because that's part of the formula of unitizing. And if you don't mind, since it's true that squaring a negative gives a positive, I'm not going to put -1 squared because that's just going to give you the same as +1 squared, okay? So this is going to be square root of 10. That's the magnitude. It's a little over 3 and some change is how long the vector is. Fine. The unit vector u, and that's traditional to call unit vectors u, but not always, but you'll see that a lot in the textbooks. You're going to take your original vector, 3, -1, and you're going to divide by the scalar, square root of 10, and then simply distribute the scalar, and we're done. And there is your answer. That's the unit vector pointing in the same direction as the original vector. Now, what if I asked you to graph that guy, you would simply plot the point, 3 over square root of 10, -1 over square root of 10, and then drawing it, and it would be, it looks something like this, where it'd be 1 unit in length, okay? Now, how would you find a unit vector that points in the opposite direction of v? No problem, it's just going to be -u. So you're just going to basically take the opposite and sign of the unit vector, the original unit vector, and so you'll just get this vector, -3 over square root of 10, and negative is a positive, 1 over square root of 10, and there's the answer for letter B. And so if I had to draw it, it would look like this. It just points in the opposite direction. Oh, that's not very nice. Okay, now these next two problems, I'm going to try to trick you on quizzes and exams because a lot of students read the directions for these two and they wrongly tell me, oh, Professor, you know what? Those are the same answer. And I go, no, it's not the same answer. You're not getting it. You need to study more. And it's in the homework too. So don't worry. I put all these kinds of problems in my math lab homework. It's in there. So we want to, for letter C, we want to find a vector that points in the same direction as our original vector V, but has a magnitude that's 8 times more than V. That's what we want to do for that guy. Now let me read the directions for letter D. Letter D, they want us to find a completely different vector that points in the same direction as V, but the magnitude is exactly 8 units. Do you hear the difference? One of them is a vector that's 8 times longer than the original. The other one, the magnitude is exactly an 8. I please make sure that you get that distinction. They're not the same. So for letter C, if you didn't already, well, letter C is easy. You're just going to go 8V because it's going to be 8 times more than your original. So you're just going to go 8 times 3 -1, and you're going to distribute your scalar. 8 times 3 is 24. That's a 24, comma, and then 8 times -1 is -8. And I claim this vector will point in the same direction as the original guy, and the magnitude will be 8 times what the original magnitude was, which is square root of 10. So in other words, this magnitude here, if somebody said, hey, find the magnitude of 8V, it's going to be the absolute value of 8, which is 8, times the magnitude of V, which we already got from part A. So it's going to be 8 square root of 10. Okay, now letter D is different. And this is where students get screwed up because they go, oh, that's going to be 8V also. No. You want a vector whose magnitude is exactly 8 units. So the first thing you need to do, step 1, would be unitize the vector V to shrink it down so that it's only 1 unit in length. And I claim we already did that in part A. So good news, we already did part of this problem already. We got the U, because what you're going to do, step 2, is you're going to just multiply that unit vector with an 8. So you're not going to multiply the original vector with an 8. You're going to multiply the unit vector with an 8, because the unit vector's magnitude is what? Somebody tell me what the magnitude of a unit vector is again?
1.
Good. So multiplying a magnitude of 1 with an 8 will give you exactly 8 units. So this is simply going to be 8 times the 3 over square root of 10, negative 1 over square root of 10, and then distribute your 8 essentially, and your answer will end up being 24 over square root of 10 and negative 8 over square root of 10. Now let me say something about rationalizing denominators here. I don't ask that you rationalize denominators in my class. Now, you may have had previous instructors that really go ballistic when you have a radical in the denominator and they want you to do what's called rationalizing the denominator. You don't need to do that in this class. This is a perfectly legitimate final answer. However, if you maybe got punished deeply when you did that and you're just thrown to always rationalize, I got to rationalize my denominators. Fine. My math lab will accept any answer. So if you have to go, okay, I need to multiply by square root of 10 over square root of 10 and then simplify, then this would look like 24 square root of 10 all over 10. And then at that point, I'd mark you wrong by 1. I'd take away 1 point from you. Why? You need to simplify your fractions. So please reduce your fractions to lowest terms in my class. Otherwise, every time you fail to do that, I'll take away 1 point. Sometimes my math lab takes away points too if you don't do full simplified. So since both of those numbers are divisible by 2, you're going to go, okay, 12 square root of 10 over 5 would be the first component, and then you would do a similar thing with the second component in order to rationalize the denominator. But I claim you're wasting valuable time. Because if it's a timed quiz or exam and you're like, oh, I got to rationalize my denominators and you don't have to, why are you doing that? You're not proving a point. Like, I'm not going to give you brownie points or bonus points for rationalizing the denominator, okay? The only time I would care is, or to simplify, is if your square root of 10 needed itself to get simplified. Like, let's say one of our magnitudes was square root of 80. I'd want you to clean that up a little bit, okay? Because I like my all my radicals to be simplified, okay? So that's kind of essentially where I'm going with this. And what we'll do next time is we'll start with the triangle inequality. I noticed a lot of you had trouble getting on the Zoom today in a timely manner, and I'm going to ask for the future. I get here a little bit early. In fact, a lot of times I'm going to be on the call at 8:15. To answer questions or homework questions, because I don't have time to answer homeworks or anything else during lecture. So if you have questions and you want to get with me sort of like a freebie extra office hour just for you, come early, okay? Come early to class and then you can get my time and attention. Also, I don't ever post solution keys for quizzes or exams. You're supposed to review that on your own in my math lab. But for students who want to see full-blown solutions, me doing them for you, I'll be happy to get to class early, maybe even a half an hour early, just for you to help you out or answer any questions. If you want to see you're like, well, I see the solution, but I still can't get it. I don't get it, Professor. No problem. Come on by and ask questions. I don't know if you're stuck because I'm not psychic. And if you just go, well, you should know I'm stuck. Well, I don't. I'm not that good. Okay, so I'm going to just open it up. Does anybody have any last minute? My math lab is weird. Should I tell you that in the case? When you say weird, Nathaniel, that could mean so many different things. I don't know.
Like from like my previous classes in particular, like what will work for like one question won't work for another. Like sometimes they will want me to rationalize it and sometimes it doesn't. Should I tell you like if I get the answer wrong in that case? Like
here's the good news, Nathaniel, because you're doing everything on handwritten work and you're uploading the handwritten work also, and I grade all the handwritten work. You're going to get the credit. Like, let's say my math lab gave you a 0 on this one problem just because you didn't simplify a radical or something, just something silly, or you didn't perfectly give what they wanted in their format. I'm going to give you your points, and I can go into my math lab and change it. And I still might take away
Okay.
1 point for you not, reducing your fraction lowest terms, but you're going to get most all of your points back. That's the benefit.
Okay, okay.
So
I-
yes, my math lab can be kind of grouchy when it comes to format, but I'm going to come in and save the day for you. Does that answer your question, or does anybody
Yeah,
have
yeah, it does.
any other questions or issues? Okay. If not, or if you're too shy, come to my 3 o'clock emergency office hour today. Please be on time on the call on Wednesday, and we'll see you guys then. Okay. Have a great afternoon.
Thank you.
Good day,
Bye.
Professor.
Thank you.
See you later. Happy days. I'm going to
Quick
stop the
question.
recording. You got it. Tell me.
Are we uploading our work for